Tantor Audio, a division of Recorded Books, presents An Introduction to Information Theory, Symbols, Signals, and Noise by John R. Pierce, narrated by Tait. Preface to the Dover edition. The republication of this book gave me an opportunity to correct and bring up to date symbols, signals, and noise, which I wrote almost 20 years ago. Because the book deals largely with Shannon's work, which remains eternally valid, I found that there were not many changes to be made. In a few places I altered tense in referring to men who have died. I did not try to replace cycles per second, or CPS, by the more modern term Hertz, or Hz. Nor did I change everywhere communication theory, Shannon's term, to information theory, the term I would use today. Some things I did alter, rewriting a few paragraphs and about 20 pages without changing the pagination. In Chapter 10, Information Theory and Physics, I replaced a background radiation temperature of space of 2 to 4 Kelvin. Heaven knows where I got that. By the correct value of 3.5 Kelvin, as determined by Penzias and Wilson. To the fact that in the absence of noise we can in principle transmit an unlimited number of bits per quantum, I added new material on quantum effects in communication. I also replaced an obsolete thought-up example of space communication by a brief analysis of the microwave transmission of picture signals from the Voyager near Jupiter, and by an exposition of new possibilities. In Chapter 7, Efficient Encoding, I rewrote a few pages concerning efficient source encoding of TV, and changed a few sentences about pulse code modulation and about vocoders. I also changed the material on error-correcting codes. In Chapter 11, Cybernetics, I rewrote 4 pages on computers and programming, which have advanced incredibly during the last 20 years. Finally, I made a few changes in the last short Chapter 14, back to communication theory. Beyond these revisions, I call to the listener's attention a series of papers on the history of information theory that were published in 1973 in the IEEE Transactions on Information Theory and 2 up-to-date books, as telling in more detail the present state of information theory and the mathematical aspects of communication. Several chapters in the original book deal with areas relevant only through application or attempted application of information theory. I think that Chapter 12, Information Theory and Psychology, gives a fair idea of the sort of applications attempted in that area. Today, psychologists are less concerned with information theory than with cognitive science, a heady association of truly startling progress in the understanding of the nervous system, with ideas drawn from anthropology, linguistics, and a belief that some powerful and simple mathematical order must underlie human function. Cognitive science of today reminds me of cybernetics of 20 years ago. As to information theory and art, today the computer has replaced information theory in casual discussions. But the ideas explored in Chapter 13 have been pursued further. I will mention some attractive poems produced by Marie Boroff, and especially a grammar of Swedish folk songs by means of which Johann Sundberg produced a number of authentic-sounding tunes. This brings us back to language in Chapter 6, Language and Meaning. The problems raised in that chapter have not been resolved during the last 20 years. We do not have a complete grammar of any natural language. Indeed, formal grammar has proved most powerful in the area of computer languages. It is my reading that attention in linguistics has shifted somewhat to the phonological aspects of spoken language, to understanding what its building blocks are and how they interact. Matters of great interest in the computer generation of speech from text. Chomsky and Halley have written a large book on stress, and Lieberman and Prince a smaller and very powerful account. So much for changes from the original signals, symbols, and noise. Beyond this, I can only reiterate some of the things I said in the preface to that book. When James R. Newman suggested to me that I write a book about communication, I was delighted. All my technical work has been inspired by one aspect or another of communication. Of course, I would like to tell others what seems to me to be interesting and challenging in this important field. It would have been difficult to do this and to give any sense of unity to the account before 1948, when Claude E. Shannon published A Mathematical Theory of Communication. Shannon's communication theory, which is also called information theory, has brought into a reasonable relation the many problems that have been troubling communication engineers for years. It has created a broad but clearly defined and limited field where before there were many special problems and ideas whose interrelations were not well understood. No one can accuse me of being a Shannon worshipper and get away unrewarded. Thus, I felt that my account of communication must be an account of information theory as Shannon formulated it. The account would have to be broader than Shannon's, and that it would discuss the relation, or lack of relation, of information theory to the many fields to which people have applied it. The account would have to be broader than Shannon's, and that it would have to be less mathematical. Here came the rub. My account could be less mathematical than Shannon's, but it could not be non-mathematical. Information theory is a mathematical theory. It starts from certain premises that define the aspects of communication with which it will deal, and it proceeds from these premises to various logical conclusions. The glory of information theory lies in certain mathematical theorems which are both surprising and important. To talk about information theory without communicating its real mathematical content would be like endlessly telling a man about a wonderful composer, yet never letting him hear an example of the composer's music. How was I to proceed? It seemed to me that I had to make the book self-contained, so that any mathematics in it could be understood without referring to other books, or without calling for the particular content of early mathematical training, such as high school algebra. Did this mean that I had to avoid mathematical notation? Not necessarily, but any mathematical notation would have to be explained in the most elementary terms. But just how difficult should the most difficult mathematical arguments be? Although it meant sliding over some very important points, I resolved to keep things easy compared with, say, the more difficult parts of Newman's The World of Mathematics. When the going is very difficult, I have merely indicated the general nature of the sort of mathematics used, rather than trying to describe its content clearly. Nonetheless, this book has sections which will be hard for the non-mathematical listener. I advise him merely to go through these, gathering what he can. When he has gone through the book in this manner, he will see why the difficult sections are there. Then he can turn back and restudy them if he wishes. But had I not put these difficult sections in, and had the listener wanted the sort of understanding that takes real thought, he would have been stuck. As far as I know, other available literature on information theory is either too simple or too difficult to help the diligent but inexpert listener beyond the easier parts of this book. I might note also that some of the literature is confused, and some of it is just plain wrong. By this sort of talk, I may have raised wonder in the listener's mind as to whether or not information theory is really worth so much trouble, either on his part, for that matter, or on mine. I can only say that to the degree that the whole world of science and technology around us is important, information theory is important, for it is an important part of that world. To the degree to which an intelligent listener wants to know something both about that world and about information theory, it is worth his while to try to get a clear picture. Such a picture must show information theory neither as something utterly alien and unintelligible, nor as something that can be epitomized in a few easy words and appreciated without effort. The process of writing this book was not easy. Of course, it could never have been written at all but for the work of Claude Shannon, who, besides inspiring the book through his work, read the original manuscript and suggested several valuable changes. David Slepian jolted me out of the rut of error and confusion in an even more vigorous way. E. N. Gilbert deflected me from error in several instances. Milton Babbitt reassured me concerning the major contents of the chapter on information theory and art, and suggested a few changes. P. D. Bricker, H. M. Jenkins, and R. N. Shepard advised me in the field of psychology, but the views I finally expressed should not be attributed to them. The help of M. V. Matthews was invaluable. Benoit Mandelbrot helped me with Chapter 12. J.P. Runyon read the manuscript with care, and Eric Woolman uncovered an appalling number of textual errors and made valuable suggestions as well. I am also indebted to Professor Martin Harwit, who persuaded me and Dover that the book was worth reissuing. The listener is indebted to James R. Newman for the fact that I have provided summaries at the ends of some chapters, and for my final attempts to make some difficult points a little clearer. To all of these I am indebted, and not less to Miss F. M. Costello, who triumphed over the chaos of preparing and correcting the manuscript and figures. In preparing this new edition, I owe much to my secretary, Mrs. Patricia J. Neal. September 1979. J. R. Pierce. Chapter 1. The World and Theories. In 1948, Claude E. Shannon published a paper called A Mathematical Theory of Communication. It appeared in book form in 1949. Before that time, a few isolated workers had from time to time taken steps toward a general theory of communication. Now, 30 years later, communication theory, or information theory as it is sometimes called, is an accepted field of research. Many books on communication theory have been published, and many international symposia and conferences have been held. The Institute of Electrical and Electronic Engineers has a professional group on information theory, whose transactions appear 6 times a year. Many other journals publish papers on information theory. All of us use the words communication and information, and we are unlikely to underestimate their importance. A modern philosopher, A.J. Ayer, has commented on the wide meaning and importance of communication in our lives. We communicate, he observes, not only information, but also knowledge, error, opinions, ideas, experiences, wishes, orders, emotions, feelings, moods. Heat and motion can be communicated. So can strength and weakness and disease. He cites other examples and comments on the manifold manifestations and puzzling features of communication in man's world. Surely communication, being so various and so important, a theory of communication, a theory of generally accepted soundness and usefulness, must be of incomparable importance to all of us. When we add to theory the word mathematical, with all its implications of rigor and magic, the attraction becomes almost irresistible. Perhaps if we learn a few formulae, our problems of communication will be solved, and we shall become the masters of information rather than the slaves of misinformation. Unhappily, this is not the course of science. Some 2,300 years ago, another philosopher, Aristotle, discussed in his Physics a notion as universal as that of communication. That is, motion. Aristotle defined motion as the fulfillment, insofar as it exists potentially, of that which exists potentially. He included in the concept of motion the increase and decrease of that which can be increased or decreased, coming to and passing away, and also being built. He spoke of 3 categories of motion, with respect to magnitude, affection, and place. He found, indeed, as he said, as many types of motion as there are meanings of the word is. Here we see motion in all its manifest complexity. The complexity is perhaps a little bewildering to us, for the associations of words differ in different languages, and we would not necessarily associate motion with all the changes of which Aristotle speaks. How puzzling this universal matter of motion must have been to the followers of Aristotle. It remained puzzling for over 2 millennia, until Newton enunciated the laws which engineers still use in designing machines, and astronomers in studying the motions of stars, planets, and satellites. While later physicists have found that Newton's laws are only the special forms which more general laws assume when velocities are small compared with that of light, and when the scale of the phenomena is large compared with the atom, they are a living part of our physics, rather than a historical monument. Surely when motion is so important a part of our world, we should study Newton's laws of motion. They say, 1. a body continues at rest or in motion with a constant velocity in a straight line, unless acted upon by a force. 2. The change in velocity of a body is in the direction of the force acting on it, and the magnitude of the change is proportional to the force acting on the body times the time during which the force acts, and is inversely proportional to the mass of the body. 3. Whenever a first body exerts a force on a second body, the second body exerts an equal and oppositely directed force on the first body. To these laws, Newton added the universal law of gravitation. 4. Two particles of matter attract one another with a force acting along the line connecting them, a force which is proportional to the product of the masses of the particles and inversely proportional to the square of the distance separating them. Newton's laws brought about a scientific and a philosophical revolution. Using them, Laplace reduced the solar system to an explicable machine. They have formed the basis of aviation and rocketry, as well as of astronomy. Yet they do little to answer many of the questions about motion which Aristotle considered. Newton's laws solved the problem of motion as Newton defined it, not of motion in all the senses in which the word could be used in the Greek of the 4th century before our Lord, or in the English of the 20th century after. Our speech is adapted to our daily needs, or perhaps to the needs of our ancestors. We cannot have a separate word for every distinct object and for every distinct event. If we did, we should be forever coining words, and communication would be impossible. In order to have language at all, many things or many events must be referred to by one word. It is natural to say that both men and horses run, though we may prefer to say that horses gallop, and convenient to say that a motor runs, and to speak of a run in a stocking or a run on a bank. The unity among these concepts lies far more in our human language than in any physical similarity with which we can expect science to deal easily and exactly. It would be foolish to seek some elegant, simple, and useful scientific theory of running, which would embrace runs of salmon and runs in hose. It would be equally foolish to try to embrace in one theory all the motions discussed by Aristotle, or all the sorts of communication and information which later philosophers have discovered. In our everyday language, we use words in a way which is convenient in our everyday business. Except in the study of language itself, science does not seek understanding by studying words and their relations. Rather, science looks for things in nature, including our human nature and activities, which can be grouped together and understood. Such understanding is an ability to see what complicated or diverse events really do have in common. The planets in the heavens, and the motions of a whirling skater on ice, for instance, and to describe the behavior accurately and simply. The words used in such scientific descriptions are often drawn from our everyday vocabulary. Newton used force, mass, velocity, and attraction. When used in science, however, a particular meaning is given to such words, a meaning narrow and often new. We cannot discuss in Newton's terms force of circumstance, mass media, or the attraction of Brigitte Bardot. Neither should we expect that communication theory will have something sensible to say about every question we can phrase using the words communication or information. A valid scientific theory seldom, if ever, offers the solution to the pressing problems which we repeatedly state. It seldom supplies a sensible answer to our multitudinous questions. Rather than rationalizing our ideas, it discards them entirely, or rather, it leaves them as they were. It tells us in a fresh and new way what aspects of our experience can profitably be related and simply understood. In this book, it will be our endeavor to seek out the ideas concerning communication which can be so related and understood. When the portions of our experience which can be related have been singled out, and when they have been related and understood, we have a theory concerning these matters. Newton's laws of motion form an important part of theoretical physics, a field called mechanics. The laws themselves are not the whole of the theory. They are merely the basis of it, as the axioms or postulates of geometry are the basis of geometry. The theory embraces both the assumptions themselves and the mathematical working out of the logical consequences which must necessarily follow from the assumptions. Of course, these consequences must be in accord with the complex phenomena of the world about us if the theory is to be a valid theory, and an invalid theory is useless. The ideas and assumptions of a theory determine the generality of the theory, that is, to how wide a range of phenomena the theory applies. Thus, Newton's laws of motion and of gravitation are very general. They explain the motion of the planets, the timekeeping properties of a pendulum, and the behavior of all sorts of machines and mechanisms. They do not, however, explain radio waves. Maxwell's equations explain all non-quantum electrical phenomena. They are very general. A branch of electrical theory called network theory deals with the electrical properties of electrical circuits, or networks, made by interconnecting three sorts of idealized electrical structures: resistors, devices such as coils of thin, poorly conducting wire, or films of metal or carbon, which impede the flow of current; inductors, coils of copper wire, sometimes wound on magnetic cores; and capacitors, thin sheets of metal separated by an insulator or dielectric, such as mica or plastic. The Leyden jar was an early form of capacitor. Because network theory deals only with the electrical behavior of certain specialized and idealized physical structures, while Maxwell's equations describe the electrical behavior of any physical structure, a physicist would say that network theory is less general than are Maxwell's equations. For Maxwell's equations cover the behavior not only of idealized electrical networks, but of all physical structures, and include the behavior of radio waves, which lies outside the scope of network theory. Certainly, the most general theory, which explains the greatest range of phenomena, is the most powerful and the best. It can always be specialized to deal with simple cases. That is why physicists have sought a unified field theory to embrace mechanical laws and gravitation and all electrical phenomena. It might indeed seem that all theories could be ranked in order of generality, and if this is possible, we should certainly like to know the place of communication theory in such a hierarchy. Unfortunately, life isn't as simple as this. In one sense, network theory is less general than Maxwell's equations. In another sense, however, it is more general, for all the mathematical results of network theory hold for vibrating mechanical systems made up of idealized mechanical components, as well as for the behavior of interconnections of idealized electrical components. In mechanical applications, a spring corresponds to a capacitor, a mass to an inductor, and a dashpot or damper, such as that used in a door closer to keep the door from slamming, corresponds to a resistor. In fact, network theory might have been developed to explain the behavior of mechanical systems, and it is so used in the field of acoustics. The fact that network theory evolved from the study of idealized electrical systems, rather than from the study of idealized mechanical systems, is a matter of history, not of necessity. Because all of the mathematical results of network theory apply to certain specialized and idealized mechanical systems, as well as to certain specialized and idealized electrical systems, we can say that in a sense, network theory is more general than Maxwell's equations, which do not apply to mechanical systems at all. In another sense, of course, Maxwell's equations are more general than network theory, for Maxwell's equations apply to all electrical systems, not merely to a specialized and idealized class of electrical circuits. To some degree, we must simply admit that this is so, without being able to explain the fact fully. Yet we can say this much: some theories are very strongly physical theories. Newton's laws and Maxwell's equations are such theories. Newton's laws deal with mechanical phenomena. Maxwell's equations deal with electrical phenomena. Network theory is essentially a mathematical theory. The terms used in it can be given various physical meanings. The theory has interesting things to say about different physical phenomena, about mechanical as well as electrical vibrations. Often, a mathematical theory is the offshoot of a physical theory, or of physical theories. It can be an elegant mathematical formulation and treatment of certain aspects of a general physical theory. Network theory is such a treatment of certain physical behavior common to electrical and mechanical devices. A branch of mathematics called potential theory treats problems common to electric, magnetic, and gravitational fields, and indeed, in a degree, to aerodynamics. Some theories seem, however, to be more mathematical than physical in their very inception. We use many such mathematical theories in dealing with the physical world. Arithmetic is one of these. If we label one of a group of apples, dogs, or men 1, another 2, and so on, and if we have used up just the first 16 numbers when we have labeled all members of the group, we feel confident that the group of objects can be divided into 2 equal groups, each containing 8 objects. 16 divided by 2 equals 8. Or that the objects can be arranged in a square array of 4 parallel rows of 4 objects each, because 16 is a perfect square. 16 equals 4 times 4. Further, if we line the apples, dogs, or men up in a row, there are 2,092,278,988,800 possible sequences in which they can be arranged, corresponding to the 2,092,278,988,800 different sequences of the integers 1 through 16. If we used up 13 rather than 16 numbers in labeling the complete collection of objects, we feel equally certain that the collection could not be divided into any number of equal heaps, because 13 is a prime number and cannot be expressed as a product of factors. This seems not to depend at all on the nature of the objects. Insofar as we can assign numbers to the members of any collection of objects, the results we get by adding, subtracting, multiplying, and dividing numbers, or by arranging the numbers in sequence, hold true. The connection between numbers and collections of objects seems so natural to us that we may overlook the fact that arithmetic is itself a mathematical theory, which can be applied to nature only to the degree that the properties of numbers correspond to the properties of the physical world. Physicists tell us that we can talk sense about the total number of a group of elementary particles, such as electrons, but we can't assign particular numbers to particular particles because the particles are, in a very real sense, indistinguishable. Thus, we can't talk about arranging such particles in different orders, as numbers can be arranged in different sequences. This has important consequences in a part of physics called statistical mechanics. We may also note that while Euclidean geometry is a mathematical theory which serves surveyors and navigators admirably in their practical concerns, there is reason to believe that Euclidean geometry is not quite accurate in describing astronomical phenomena. How can we describe or classify theories? We can say that a theory is very narrow or very general in its scope. We can also distinguish theories as to whether they are strongly physical or strongly mathematical. Theories are strongly physical when they describe very completely some range of physical phenomena, which in practice is always limited. Theories become more mathematical or abstract when they deal with an idealized class of phenomena, or with only certain aspects of phenomena. Newton's laws are strongly physical, in that they afford a complete description of mechanical phenomena, such as the motions of the planets, or the behavior of a pendulum. Network theory is more toward the mathematical or abstract side, and that it is useful in dealing with a variety of idealized physical phenomena. Arithmetic is very mathematical and abstract. It is equally at home with one particular property of many sorts of physical entities, with numbers of dogs, numbers of men, and, if we remember that electrons are indistinguishable, with numbers of electrons. It is even useful in reckoning numbers of days. In these terms, communication theory is both very strongly mathematical and quite general. Although communication theory grew out of the study of electrical communication, it attacks problems in a very abstract and general way. It provides, in the bit, a universal measure of amount of information in terms of choice.
Sample complete. Ready to continue?